from the current slide. Okay. I don't know if any of you are interested in this kind of stuff, but let me tell you a few adjustments to my schedule in case you need to know this for future. Now, a couple of these are just temporary one-day type things. Another one is big for the rest of the term. Okay, first, if any of you are looking, I'm talking to people listening to this too, are looking for me tomorrow during office hours. Normally my office hours on Tuesdays and Thursdays are 11:15 until 1:15. Not tomorrow, okay? Tomorrow I'm taking my physical science class to a field trip, so I have to come over here to the East Campus, pick up a vehicle, and take it back to the Bessemer campus so we can go on the field trip. So that means that I will not be in the office from 11:15 pretty much until probably around 12:30. It takes me at least 30 minutes to get there and back, and then maybe 15 minutes to get all the paperwork done. Though I've done most of the paperwork, sign out and all that kind of stuff. So I'm figuring I'll be there from 12:30 until 1:15. But at 1:15 we got to leave sharp to get to the field trip on time. So very limited office hours tomorrow, 45 minutes rather than 2 hours. Okay, but on the good news, because we don't have a lab tomorrow, we'll probably be back from the field trip around 4, and then a few of the students still have to take either the last test and final or just the final exam. That won't take them too long, I don't think. So that means that we'll be, already marked you here. I did it by mistake. So I was psychic. So, okay. I'll reinforce that. Okay. Good deal. Thank you. So even though I lose some office hours in the front part, 11 to 12:30, 11:15 to 12:30 or so, hopefully I'll get some back at the end of the day, maybe from 5 to 6 or something like that. So it may even be earlier than that. So that will be office hours tomorrow. Now, I don't know if y'all are aware of it, maybe you don't care, but tomorrow is the coronation day for Miss Lawson State, so there's a big to-do going on most of the day tomorrow, and including 7 o'clock tomorrow night when the big thing happens, and that'll be at the Bessemer Civic Center in case any of you are wanting to go. It should be a very nice event. Okay, so that's tomorrow. Friday, we've got to go out of town, and I just found out this afternoon what times various things are happening Friday in Atlanta that we need to be there at least for part of it. It looks like I'll be able to stay until my 12 o'clock leave time, but in case my wife said, no, with traffic and all like that, we have to leave a little early, I might have to leave. So normally I'm Birmingham office hours over on the Birmingham West Campus on Fridays are 8 to 12, but I can't stay any past 12. Most Fridays I'm there well past 12. Can't stay any past 12 tomorrow and may actually have to leave a little early. So there's that one. Monday should be about as normal as any Monday is, so I don't know of anything happening then. But Tuesday, 2 things are happening. Number one, I've got a doctor's appointment at 10:40, which means I have to be at the lab at 9:40 to do for blood work, which means I have to leave campus no later than 9 o'clock. So normally I'm in class at 9 o'clock, and so my 8:30 class will be shortened, and my 9 or 10 o'clock class will be wiped out completely. Okay, but normally I have office hours again from 11:15 until 1:15. Okay, I'm almost certain with my appointment at 10:40, I won't be leaving the doctor's office any before 11 o'clock. In fact, I doubt if I can make it by 11. But that would be the earliest I'd be able to get away, and that means 11:45 before I get back to campus. So I won't be in the office almost certainly at 11:15, probably at least for another 30 minutes, maybe longer than that. But now this is the permanent change. And by the way, first mini-term is over this week. This is the last week for first mini-term, meaning second mini-term starts next week. Now that means two things. Are any of you in a mini-term class? I take probably not. Okay. And you won't have to worry about student course evaluations for that. But the second thing is they usually ask for us to do midterm progress reports on students. Y'all are all in good shape. Those of you who have been coming and turned in your test, which is everyone here. But some of the people not here, I'm talking with on this, if I don't have a grade, I've got to turn in a midterm progress report on you that you're failing at midterm. Now, that doesn't cost you anything, but it just means someone might be getting in touch with you from the counseling office or somewhere to see if you need any support to clear up those issues. All right. Let me get your name, please. Caitlin? Yeah, okay. All right. Good deal. And so that's the first issue with mini-terms or midterm progress reports. The second issue, well, I've taught first mini-term class, and that's on Tuesday, Thursday. Started at 1:15, ended at 5:45 because it's a physical science class, 2.5 hours of class, 2 hours of lab, both days. Long time. Second mini-term class, though, I can't start as early because the automotive students, some of them take that course as well, and they're in a block schedule. They're in class from 1 to 3. So I can't start their physical science class until 3:15. So that means my office hours on Mondays and Wednesdays, or Tuesdays and Thursdays now in the future will be 1:15 to 3:15, a full 4 hours of office hours, which will be extended, and I can sure use it. The bad news of that situation is I go till 7:45 in the evening, so it'll be a lot longer days. All right, that's most of the changes I know about. Do you have any questions on any kind of stuff, including what we've done so far? Yes. Okay, the second test. Okay, let me get that for you. Okay. All right. Oh, that's the wrong test. Okay. All right. I don't think there are any changes to be made on this one. Did I give y'all any changes on the second test? Okay. All right. Oh! Sorry, I'm old and slow. That's the second test. All right. Yes.
When you're doing when you're trying to get straight,
Right.
is there ever a time that you would use the weight such as 32.2 on it, like when you're using the when you're using meters, and I'll use the 9.8 when you're using the metric system.
Okay.
So I wonder, is there any time that you could use the United States?
Okay. Okay, so basically, how do they define the stress force per unit area, right?
Right, but I'm just wondering
Right.
use.
Yeah, okay. Now, the forces are always either in pounds or newtons. In newtons, you use the 9.8, and in pounds, you use the 32. 32.2. Okay. Okay. So if your problem was all strictly in U.S. Whatever they call that, standard or customary units, which are pounds and that, then you would. But your area would also have to be in that. So that would be probably pounds per square foot or pounds are in that, and they give you a weight and a, let's see. The only time that I can think that if they gave you a mass in slugs, which they don't usually do, then you would use the 32.2. But they don't usually get that. I know they don't. Yeah, okay. Yeah, because you see, pounds is already the force. Kilograms is not a force, so that's why you have to use the 9.8, because you have to get it into a force unit newtons. So I can't say never, but I think it'll be very rare that they'll ask for something they'll give you something in slugs. They just don't do that. All right, good question. Any others? Okay. Where we are is in chapter 12, and the section in chapter 12 is 12.3, properties of liquids, and we were talking about these last time, and we were talking about capillarity, okay? So this is a slide that shows a comparison of different fluids. Typically for water is very strong cohesion, that's between like molecules, water to water molecules, very strong, but also very strong adhesion, which water attracts to other materials, like glass, plastic, and things like that. So the comparison of capillary action of water and mercury. Water very much tries to climb a capillary tube because it's attracted to the sides of the tube, and as it's attracted, then its surface tension pulls up the rest of the water molecules. So it actually will move up a capillary tube. This is a relatively large capillary tube, a medium-sized capillary tube, and a very small capillary tube. So the diameter of the tube also determines how high the water is lifted. Okay? Now, we're not going to mess around with the formulas with that. That's beyond the nature of this course, but just the fact that it happens. And you can see always the surface, what they call concave. Lower in the middle and rises on the side because that action between the water and the sides is what pulling the water up. Okay? Water is attracted to it, so it pulls it up. So it's always concave. And you can sort of see it here. It's not real clear, but you can see that. Okay? Now, in very thin tubes, the water stands at higher levels, and the water is always concave at all of those levels. In very thin, okay, now let's do mercury on the other hand. Mercury, very strong cohesion. Those molecules hang on to each other really tightly, as do waters. But the difference is mercury doesn't like to combine with anything else. So therefore, it tries to repel the glass. And as much as possible, it gets away from the glass to the extent that it pulls to the inside and trying to get away from the glass on the outside. So now you have a convex top. Now what they call this, I'm surprised this book doesn't use a term. This is called the meniscus. The lowest point here, the highest point there is called the meniscus. Okay? And mercury always has a convex meniscus. And with a fairly large tube, it just pulls it down a little bit because it's trying to get away from the sides of that tube. See, it's doing it on the outside as well, okay? In a smaller capillary tube, it pushes down even further, and in a tiny tube, it really pushes down. So the mercury's, in a very thin tube, mercury stands at lower level. That's a weird way to say it. The mercury surface is convex. The tube diameters and the differences in liquid levels are exaggerated in both of these. I've never seen one go up that much, okay?
So it takes the same shape on the outside as it does on the inside.
What's that now?
It takes the same shape on the outside.
Okay. Yeah, what it does, if you put this capillary tube into a pool of mercury, this mercury goes down here too. Now, it doesn't do as much because it's the outside of the tube. It doesn't have the capillary action there. You know, the capillary action, the smaller the tube, the more it pushes down or picks up if it's water. But the outside of the tube, you got a lot bigger area there, so it doesn't push down as far because it has to drag everything down. Okay. So does that make sense, sort of? And none of you are nurses, is that right? Okay. Yeah. Yeah, okay. Your thermometers, there's two basic kinds. Well, nowadays there's all sorts of kinds. But in the old days, there were either red liquid in it, and that was a clear giveaway. That was alcohol thermometer, or colored water one. And generally, that had a concave meniscus because it was alcohol or water, tends to pull up. But the mercury thermometers, which are the harder ones to read in my mind, but they're probably considered more accurate, I don't know that, but they had the convex. You always tried to read the meniscus, whatever the top of that curve was or the bottom of the curve. And they scaled it for that purpose. All right, so that is the figure on page 327. All right. Wow. I think what I need to do now is to go to the other slide, because I think I'm going to have to do some writing on that. So we'll go from the current slide here. All right. Toward the top, there it is. I knew they had to address it somewhere here. On the top of page 328, you'll see the crescent-shaped surface of the liquid column, whether convex or concave, is called the meniscus. Just wasn't on that other slide. Okay? And everything else I just said. Now, experimentally, I don't know if you're interested in this, scientists have found that three facts here. Liquid rise in capillary tubes, they tend to wet, and are depressed in capillary tubes, they tend not to wet. So in other words, water, which tries to wet the tube, is pulled up the tube, whereas mercury, which resists like everything wetting the tube, is pushed down. Okay? We've already talked about that. Number two, elevation or depression in the tube is inversely proportional to the diameter of the tube. We illustrated that as well, and I wish I'd had that other slide still up. And then number three, the elevation or depression decreases as the temperature increases. The elevation or depression decreases as the temperature increases. Now, why is that? Well, as the temperature increases, the molecules move faster, so they don't tend to stick or repel the sides of the tube as much. So it would reduce both of them. Okay, then there's a physics connection listing there on viscosity, and they talk about oil viscosity. I think we mentioned that in class, and so you can just read that. There are absolutely no problems in 12.3, okay? No formulas and other things. So let's move to 12.4, the properties of gases, okay? Now, I'm going to talk about a couple of these. I'm going to hit the words that they bold, because I take it they think those are the most important. First, we've already talked about this before. What makes a gas is that it tends to expand. So a gas is said to be expansive. No, expansion. The property it has is expansion, I-O-N. Okay? Okay. Now, solids and liquids also expand when they heat, generally, but it's not very much. They contract when they cool, but it's not very much. But a gas expands. I mean, it just takes up the whole volume. That's what makes it a gas. Remember my illustration of the ammonia bottle in the corner here. If I were to open it up and then think of some excuse I had to leave the room, after a while your eyes would be, because that ammonia is just going to fill the whole room. And soon Dr. Marable was saying, "What are y'all doing in there?" Okay, never mind. So, all right. So that's one feature, a property of a gas in which the rapid random movement of its molecules causes the gas to completely occupy the space in which it's located. Okay? Now that also makes it dangerous if you have leaks. Okay? For instance, a natural gas leak. These molecules are going everywhere. So just because the leak might be in the basement, you could strike a match, or light something in the kitchen and still have things blow up, okay, because the gas tends to go everywhere. And that's why for natural gas, which, by the way, is odorless, they add a really obnoxious odor to natural gas, so that if you smell it, that's not really the natural gas, that's what they added, then you know to shut things down and get out of there until they find out where the leak is. Okay, so that's expansion. Okay, another feature of a gas, and this holds for other materials as well, but much more for gas, is diffusion. Now, you might, on the surface, think of these as pretty close, and actually, they tend to relate to each other well. Okay? What diffusion is, are any of you gardeners? No? Okay. Well, that's too bad. I enjoy raising, especially vegetables, so we don't have a place where we're living now that is comfortable to do so. So we do ornamentals and things like this, but not to a huge degree, but just some. And as I've noticed in our gardening, sort of a dumb example, Bermuda grass goes from levels of high concentration, the yard, into my flower beds or into my vegetable beds like crazy, okay? And that's, to me, an example of diffusion. Diffusion is going from an area of high concentration to an area of low concentration. Lots of Bermuda grass in the yard, and that's where it belongs, but you plan to put a bed around there, it's going to try to get in there as much as it can. Now, that's a dumb example, but that's an example of diffusion, going from a high concentration to a low concentration. And that's what gases do. And by and large, that's why the expansion occurs. Because I open that bottle of ammonia, high concentration of ammonia in the bottle, so those gas molecules are going from the high concentration to the low concentrations like crazy. Okay? So that's what diffusion is. It's the process by which molecules of a gas mix with the molecules of a solid, liquid, or another gas. Now, they don't really mix that much with solids and liquids, but they do some. If you remove the cap from a can of gasoline, you soon smell the fumes. Okay? The air molecules and the gasoline molecules mix throughout the room because of diffusion. Okay? Now, I said they don't do it as much in solids and liquids, especially solids. But liquids, they do. Okay? If you were to open let's say the bottle of ammonia, the bottle of gasoline, can of gasoline, whatever, in, say, a closet or a cupboard where you had your sandwich in there that you were going to eat for lunch, when you take that first bite, you're going to taste that, or have in there where your water is located, you're going to taste. In fact, in refrigerators, if you ever have something open in there that does smell pretty strongly, like garlic or something, but you also have an open glass of water for some reason you put in there to keep cool, the odds are when you go to drink that water, what's that taste, because that odor, which is a gas, molecules are going to infiltrate the water as well. So that's why things will pick up taste in a refrigerator and sometimes even a freezer. Okay. Now, here's another definition. I'm going to first ask you what you think it is. What in the world is a fluid? Tell me. What's another word, a synonym for fluid? Second? Okay, that's what just about everyone thinks. In physics, a fluid is either a gas or a liquid. Not a solid, but a gas or a liquid. So anything that can diffuse or mix easily is a fluid. Gas or a liquid. So we say here, the behavior of liquids and gases is often similar. A fluid is a substance that takes the shape of its container. Solids don't do that. liquids and gases do. The term is used when discussing principles and behaviors common to both liquids and gases. The same principles that conduct the air and the ventilation system are the same principles that do water in a pipe, blood in your veins. You know, it's the same principle for all that. Okay, that's fluid flow. Liquids or gases, doesn't matter. Solids don't move that way. Okay, so that's why it doesn't fit. Okay, now that was 12.4. That was it, folks, what we just did. Properties of gases. There are other properties, but this book doesn't cover them. So let's not belabor them. Okay? Let's move on to 12.5, which is a characteristic of any material, and that's called a density. Okay. So a fluid, either a liquid or a gas. Okay. So density. Density is a property of all three phases of matter: solids, liquids, and gases. Okay? Now, there's two types of density. The first of these is a mass density. And most of the time when we're dealing with the SI units, System International, the metric system, this is what we'll use. And mass density is the mass per unit volume. And, okay, I was going to use the symbol they usually use, but this book doesn't use it. In fact, they don't use capital M, they use little m. So let me correct that just a little bit. The symbol they use for mass density is a capital D sub M, mass density. And what that is the mass. They use a little m per unit volume. That is a capital V. Does anyone know why it's a capital V? That symbol. What does little v stand for? Velocity. You're absolutely right. So capital V is the parameter for volume. Little v is the parameter for velocity. So that's it. Now, there is another type of density, and this is weight density. Now, you can use weight density in the SI system. Most of the time we don't, but we mostly use weight density in the U.S. customary system. They used to call it the British system. British don't officially use it anymore, though they still commonly use it. And this is density sub W for weight density, and that would then be weight per unit volume. Okay? Now, this book doesn't use weight. They use F sub W. Force in a weight sense, the force due to weight. Okay, so they use some strange terminology, but that's what it is, the force due to weight. Okay? Now, the force due to weight, does anyone remember its formula? This is just a review question. Mass times the acceleration due to gravity. Now, in the U.S. customary system, we never use mass, so we don't usually use that. But if we were using weight density in the SI system, but they gave you kilograms, but they wanted mass weight density, you multiply the mass in kilograms times G, 9.8 meters per second squared. All right. And the main reason the U.S. system doesn't usually use mass density, no one uses slugs, okay? You don't use mass usually, okay, in the U.S. customary system. All right. It says conversion factors must often be used to obtain the desired units, and I think y'all discovered it. I heard y'all talking about it. The conversion factors are in the back of the book, and there are tables back there beginning on page 686, I can't read, through, there's just about anything you can imagine that you could convert. 689, continuing. Well, not all these are conversion. Some of them are just tables. But some of them are conversion factors, basically through 691. Some of those are just tables, okay? But that's where you can find many of your conversion factors if you need them. Now, one table I saw back there when I was just doing is also here in the text, and this is where I will discard this and go back to this one. All right. And that was this table. Here are some of the common densities for various substances. Now here's a key about densities. Density is a characteristic of a material. If you have iron, pure iron, if you have an ounce of iron, if you have a pound of iron, if you have a kilogram of iron, if you have a metric ton of iron, the density is still the same because it's mass per unit volume. If it's iron, it has the same density. Okay? Same thing for water. Whether you have a thimble full of water, a glass full of water, a tank full of water, an ocean full of water. Okay, that would be salt water, so a little bit of difference there. But the density is always the same. It doesn't matter the quantity you have because it's mass per unit volume. So these are numbers that would be good for whatever. Now, they give the mass density in kilograms per cubic meter. I found that a big blue hiss, okay? Because a cubic meter is a huge volume. Much more common would be a cubic centimeter. But SI uses meters, so that's why they give them. So the numbers are way too big, okay? And if you're doing mass density in the smaller unit, it would be gram per cubic centimeter. Those are very reasonable units there. The weight density, pounds per cubic feet, again, a cubic foot is a pretty good size, so these are still pretty good sized numbers. But what I'm used to using is grams per cubic centimeter. Those are the ones that are most common to me, okay? And all you do to get from mass density in kilograms per cubic meter to grams per cubic centimeter is move the decimal 3 places to the left. That's all you do. Instead of the comma, put in a decimal, okay? It's so easy to do. And those are much more usable numbers, 2.7, 8.7, 2.3, rather than 2,700. You know, that's such a big number. Okay. All right. Now, a few things to note. Aluminum. I don't think your book has a periodic table. I can't remember finding it. It's a very light metal. That's why, in general, most aircraft are made out of much more aluminum than they are steel. There's very little iron or steel in an airplane because they want it as light as possible. Now, a lot of vehicles, in fact, maybe some of the vehicles you drive, because car companies were being required to go get much better gas mileage. One way you get better gas mileage is to make the vehicle lighter. So a lot of vehicles were going to aluminum rather than steel. What's that? Oh, there's a periodic table. What page is that on? 694. Okay. It may be my physical. No, I'm science professor. 694. So it's just after where I was looking, sending you to. If I'd have just turned another page or two, I would have found it. Okay. There it is, 694. Okay? I'm going to lose something out of here if I'm not careful. Okay? Aluminum is right there. Looking at it upside down. One of the lightest metals going. It's AL, number 13. Okay? Most of your other metals, like iron, that's down here, it's number 26. Okay? Basically, about twice as massive as aluminum. Okay? And you can go on and find other things. Now, one thing I found a little surprising about this table is they include something they call brass. And maybe brass has a specific thing, but brass is an alloy of copper and zinc, I think. It's an alloy. So it's a mixture of things. So why can they say this is the mass density if you're mixing things together? It's not a compound, which goes by definite proportions, but a mixture. So maybe they have a standard brass and this is what it is. Now concrete's another thing that's an approximate number. You can have concrete that has more cement in it and less sand, or more sand and less cement, or concrete with gravel rather than sand. So that would change its density a little bit, not a whole lot. So that's sort of an average. Copper, though, that is actually a metal, an element. So that's going to be very precise there. Cork, again, cork is it's a type of wood from a cork tree. It's just very porous wood. So more porous would be less dense. Okay, so that's not, but these are just average numbers. Now ice, that's pretty close to it because pure water, pure ice, that would be pretty close. Okay, iron, that's another element, so that would be right on the money. Lead, another one. Now notice here, lead is one of the densest metals we have. Not the densest, but one of the densest. Now here's wood, white pine. Again, that's an average number, because wood is not an element or a compound, it's sort of a mixture. Liquids, alcohol. Well, you have many different kinds of alcohol, but on average it's about 790. Gasoline about 680. So when you have gasoline with ethanol, which is alcohol in it, that's going to increase your density just a little bit. But then look at mercury. Mercury is an element. It's a liquid at normal temperatures and pressures. And look how dense it is. 13,600 kilograms per cubic meter. That would be 13.6 grams per cubic centimeter. Lead would float in mercury, and does float in mercury. Amazing that lead would float in a liquid. But that's because that's a heavier metal. And if you find mercury on the periodic table, you'll see it's much further down than lead, or a little bit further down than lead. Oil is more like gasoline, actually more like alcohol, but it's a little denser than gasoline. So it's in that range. Seawater, a little bit denser than plain water, pure water. Okay? Now, here's the thing. They put a bar over that zero. If it's pure water, it's 1,000.0000. I mean, as many as you want, because pure water, by definition, that is its density. 1 gram per cubic centimeter or 1,000 kilograms per cubic meter. So I don't know why they put the bar over that. But you see, seawater to 1 decimal place is the same, but to 2 or 3, it's a little more dense. Why is that? It has salts dissolved in it, and they are denser than water. Okay? And again, that's a mixture, so that's not an exact number, but it's an average. Now, most gases, okay, now you have to specify the temperature and pressure, because gases expand really greatly. Remember, we talked about that. On average, air, which is a mixture of gases, mostly nitrogen, then oxygen, and then all the others, carbon dioxide, water, methane, whatever, it's about 1.29 kilograms per cubic meter, okay? That would be 0.00129 grams per cubic centimeter. And here's Tyler. Now, something I was mentioning earlier, let me say again, because you may not go back and listen to what I said earlier. This is right at the end of the first mini-term. Sometime this weekend will be the middle. And then next week starts the second mini-term. That means that we're right at mid-term, okay? And they usually ask for us to submit midterm progress reports, which means I need grades from everybody, okay? If I don't have one, I have to put down you're failing at midterm. Not that that hurts anything or anybody, but someone may be getting in touch with you saying, oh, you need tutoring or counseling or something else. So if I can get at least one of your tests in before.
Yeah, I got to get my book. I was looking at that stuff. I can't. Dude, I got to go get my book.
Yeah.
That in the math class.
Right. Okay.
I was going to talk to you about my math stuff tomorrow.
Okay.
Because I got another job. Sometimes I got so many classes. It's hard for me to.
I know. Okay. All right. So we're talking about density. You don't have a book either, but we're on page. If and when you get it and you refer to it, page 330 is where this table is located. And we're just talking about the gases. And here ammonia, much lighter than most air. Carbon dioxide, denser than air. Okay? Carbon monoxide, closer to air, actually a little less dense. Okay? Helium, the lowest density of any substance. No, I'm sorry. Hydrogen is actually less. Hydrogen is 0.0899 kilograms per cubic meter. So that would be two more zeros in front of that zero. That would be a terribly small number. Nitrogen is 1.25, and oxygen 1.43. And propane 2.2, 0.02, sorry. Now, here's why I mentioned these. What part of air do we need? I just gave it away, didn't I? The oxygen, okay? It's here about 1.43. So a little bit denser than most of the other air. The reason for that, most of air is nitrogen, is that see, nitrogen and air are almost the same density because most of air is nitrogen. Okay. Now, carbon dioxide, though, a lot denser. I mean, not that much, but a little bit more. If you're in an environment, say, where there's a fire or smoke-filled room and stuff like that, generally, the better news is to get, for carbon dioxide purposes, stay high. However, for smoke inhalation, go low, okay? So you're kind of at a problem there. If you're running, if there's been something depleting the oxygen in a room, get as high as you can because that's where the oxygen is going to be compared to the carbon dioxide. However, if you're in a room with a leak, say, of ammonia, then you want to get low, down where the rest of the air and the oxygen are, not up high where the ammonia is. So you have to play around with these things. It's just there's not usually that much there. And I thought that, oh yeah, propane. If you had a gas leak, now that's not the only gas you have, but if you had a gas leak, then you want to stay up because the oxygen is less dense than propane. Getting down is not a good idea. Okay, so some are up, some are down, so it's really hard to say what would be the best move unless you knew what was in the room. But those are just examples of densities, mass per unit volume, and these are characteristic of these materials. Okay, that is the last slide in the chapter. So what we'll do is go back to, if there are no questions on that, wanted to point out two more things, especially with regard to water. I already mentioned water is less dense than salt water. So any of you ever been on a boat that goes both out into the Gulf, say, but also goes inland? If you have been, these are called medium-sized craft that can either go in. You'll notice on the water line, they have two separate scales, one for fresh water and one for salt water, because in fresh water, they sink lower than they do in salt water because they have to displace their weight, and because in salt water or seawater, it's more dense, so they don't have to displace as much volume. Okay, another thing here This is the interesting one I think we've mentioned before. Water is denser than ice. And you know that already. Do you have any ice in your cup? Probably melted. But when you first had it in there, did you have water in there or some sort of other drink? Huh? Just ice? What's that? Just ice. But when it started melting, where did the ice go? It floated and the water went down below, right? Your straw, you were able to suck the water out. If you're up in the ice, you're getting mostly air. Okay? Ice floats. That's one of the few, if not only, solids that are less dense than their liquid. Most other things, when you solidify something, it gets smaller, not water. Okay? It actually expands when you solidify it. So, because of that, we have life on the planet. Believe it or not, that little fact. If ice was denser than water, then any place, a river, a lake, or anything else in very cold weather, when it would start freezing, it would freeze from the bottom up. And all life in that river or lake or stream or whatever, it was dead. Okay? Because it can't do it. But because ice is less dense than water, it's up here and there's water underneath, liquid water underneath, so plants and animals can still live down there. And in fact, there's usually a pocket of air in between because as ice has risen, air that was trapped gets in there. And believe it or not, if that happened in the cold environments, that would affect the whole rest of the ecosystem. We wouldn't survive. Okay? It sounds extreme, but it really is true. Okay, so let's end this one and go back to, where is it? There it is, I think. Yeah, there it is. Go back to the one we can write on. All right, example 1. Find the weight density. Remember what the symbol for weight density was? D sub W, right. Find the weight density of a block of wood. The block of wood is 3.00 inches by 4.00 inches by 5.00 inches. That's a very precisely cut block of wood, okay? I'm sure they didn't do that with a chainsaw, okay? All right. With weight of, and what was the symbol for weight? Say again? F sub W, perfect. The weight was 0.700 pounds. There's its weight. So we're looking for density. What is the formula for density? Weight density specifically. Anyone remember? F sub W divided by volume. We got F sub W. What's the volume? Didn't give it to us, did they? In so many words, but they actually gave us enough we can calculate it. If you have a rectangular solid like this, and you have the width, the length, and the thickness, you can calculate the volume, right? Length times width times height. So, do it. What is the volume of this one? To me, the easiest way to do it is multiply 5 times 4 is 20 times 3 is 60. So that would be 60.0, and your units are cubic inches. All right. Now, the big boo hiss here, they're wanting this in pounds per cubic feet. To me, pounds per cubic inch would be perfectly fine, okay? But they want it in pounds per cubic foot. So how are we going to get cubic inches to cubic feet? Okay, not a bad idea. Why 12? 12 inches in 1 foot. You just did your conversion factor there. But what do you notice is different here? This is inches cubed. That's just inches. That's feet cubed, cubic feet. So you have to cube this, and cube that, and cube this, which I can do without too much problem. 1 times 1 times 1 is 1. But you also have to cube that. 12 by 12 by 12. Sounds like a job for a calculator to me. So 60 divided by, and then you can do it any way you want to, 12 cubed. Most calculators will do that if you know how to do it on that. If you don't know how to, then just do 60 divided by 12, divided by 12, divided by 12. You know, do it 3 times. Or 60 divided by, and then put in parentheses, 12 times 12 times 12. And then close your parentheses. However you do it, what do you get? Anyone know it? It's going to be a pretty small number. 0.04? Is that all you get? A bunch. Say again? 0. Is there a 0 between the decimal? 0.0469? Yeah. Okay. 469. What was the next digit? After 9. Hey. 4. Yeah. Well, then you rounded correctly. Cora, right? Okay. Got to find you though. There you are, below the blue line. Good deal. Okay. So 0.0469. Now, if you got it on your calculator, you can leave it there, because what you can do then is do your weight of water, 0.700 pounds divided by 0.0469, and if you had those other digits, divide by all of them. I don't care, but this will at least give you cubic feet. And what does that number wind up being? It's between 10 and 20, right? No, yeah. No, a little over 20. Is that a 4? Yeah, I think our conversion there is not quite right. 60 divided by 12 times 12, well. Yeah, and multiply. 12 times 12 times 12, what does that give you? 12, second? Okay, 12 times 12 times 12 is what? I don't hear well, sorry.
Oh, 17. Look.
That's it, okay.
I looked at it wrong.
Okay.
I got my numbers backwards.
All right. So what does this give you then? What did you get? Second?
1720.
Yeah, I looked at my numbers backwards.
Okay. You got 1728 here. Is that right?
Yeah.
So what is it when you do 60 divided by that? Say again? 0.034?
Yeah.
Okay, I need another digit at least.
0.0347.
7. Okay, the next one is something. Okay. Okay, good. All right, so that's you divide by 0.347. Let me erase it. Okay. The reason is the numbers weren't coming out right. 347. Okay, that's going to be something a little bit greater than 20. And what do you get? 0.7 divided by 0.0347. Second? 20.17. That would be pounds per cubic foot. but we only have 3 significant digits, so let's round that to 20.2 pounds per cubic foot. I left off my cubic foot. Okay, and that's what the book got. Okay, now let's look back at the table. This was wood, and they did show some wood there. They said white pine, they said was 26. So this must be a wood that's lighter than white pine. I'm really going to make a guess here that might be something like cork, maybe not that light, or bamboo. That's usually light too, so something like that. But it's not white pine. And white pine is usually not that dense either, so it has to be a really light wood. All right. Any questions on that? That was example 1 in section 12.4, is it? 12.5. Okay. Can I erase this? Because I'm afraid we won't have room for the next one. Okay. So let's erase that ink. And it says now find the mass density. What's the symbol for mass density that this book uses? D sub M. And by the way, just so you'll know this, the symbol that most texts use for density is something called rho. It's a Greek letter, rho. Why they use rho, I do not know. But most texts use rho, not dm and dw. Okay? So I'll erase that for now. But just to let you know. If you see rho listed, usually that's the density. So find the mass density, this is what we're looking for, of a ball bearing with a mass equal to 22.0 grams, okay, and a radius of that ball bearing is 0.875 centimeters. Okay. We want the mass density of that. Now, frankly, I'd be very happy to use these units, grams per cubic centimeter. But to get the kilograms per cubic meter, basically all you do is move the decimal 3 places. So let's go on and calculate it here. What's the definition for mass density? The formula, equation. Mass per unit volume. Do we know volume here? No. What they gave us is radius. So what is, and by the way, what is a ball bearing? Y'all have seen them before. It's a little sphere, a little ball. That's why they call it ball bearing, right? Okay. Now, I'm not as familiar with this book as others. I'm sure somewhere, I'm hoping they have a list of your common physical shapes that you can get those formulas for. But right now, I'm not seeing it. Oh, here it is. Here it is. Back inside cover of your book. Okay? And you see the sphere at the very bottom. See it? And there are 2 formulas for volume, 1 for area. And since we were given radius, we're going to use that first one. What is the volume of the sphere? Anyone see it? You found it in the back of the book? Okay, what is it? Second? 4/3 pi r cubed. Okay? Now, I'm just going to make a guess now. I bet you most of your calculators have a pi key, don't they? If they don't, you can use 3.1416. That will give you as much precision as you'll need. So what we're going to do here is do 4/3 times pi, and I'll let you figure out the pi key, times 0.875 centimeters cubed. So here we have to cube again. Be careful when you're doing it. That's 0.875 times 0.875 times 0.875. That you should be able to do pretty easily. 4 divided by 3 times pi times 0.875 times 0.875 times 0.875. Unless you know how to do a cube key, which is pretty easy to do too. So you could do that. I'll show you if you need to know. That's going to give you the volume.
Would it be EX?
Second? Not e to the x. Some calculators will have a cubing key and some will not. Let me take a look. Here's a square key. So here's the one you use that key right there. It's called the caret key. For those of you who have calculators with a caret key, here's what you would do for that formula right there. You would do 4 divided by 3 times whatever your key is for that, pi if you have a pi key, times whatever key you have for a times, 0.875, so you don't need to write the 0.875, then do the caret key, and then do a 3, and then press equal. Some calculators will have that key. Some of the older calculators will have a key that says something like a raised to the b or x to the y or something like that. This is the one that her calculator has. What do you get?
2.8.
Second?
2.8.
2.8 what?
806.
8 what?
06.
06. So we'll do 2.81 is what you said. You can do the 06 if you want to, because that'll give you a little more precision. And that will be cubic centimeters. Okay? So what we're going to do now is the mass, 22.0 grams, divided by the volume, 2.81 cubic centimeters. Then do your calculation with that. And what do you get? Anybody?
7.829.
Okay, 7 point what?
7.83.
83?
Yeah, well, it was 829.
829. So 7.83 grams per cubic centimeter. Now, I've already told you the easy way to get to kilograms per cubic meter. Just move your decimal 3 places. 7,830 kilograms per cubic meter. Okay? Now, I want you to look at the table and see what material has a density very close to that. Second? Second? Iron, you're absolutely right. And most ball bearings are predominantly iron. Now, they may be totally iron, and that wouldn't be far off, but sometimes, I probably should have put my comma in there, sometimes they're mixed with other things to keep them from rusting, because you don't want your ball bearings to rust. And that may be chromium or something else that may affect the density a little bit. Often we call that stainless steel, because stainless steel should not rust. Okay? That's why they call it stainless. All right. And they got the same thing you did. Good for you or them or whoever. Okay? That was example 2. Ready for example 3? Now you can do it all at one big time. That's what the book tends to do. Or you can break it down into smaller steps like we've been doing. However you want to do it. I just think this is a little easier to see and think through. But can I erase? Okay. Example 3. Find the weight density, that's the D sub W again, of a gallon of water weighing 8.34 pounds. 8.34 pounds. Okay? Now here, what is the issue here? We've got the weight, which is what we need. We don't have a volume. They gave us a capacity of 1 gallon. Okay? Now this may be a good place to check out your tables at the back of your book. Okay? I think I'll mark my place right here because I get tired of trying to do it with my fingers. Okay? Let's go to the very beginning of that and see what we got. U.S. weights and measures. Okay? Time, speed, force, power, pressure. You know, I'm not seeing it. Do you? Nope, not seeing it. So I bet you it's somewhere in the text, and that's harder to find. So let's see. Okay, we already know the weight. What we want to do is the relationship between volume and capacity. I'm just checking to make sure I haven't missed it. I do not see it. Conversion table for volume. I thought that would be, I think I found it. Yeah, table 4 maybe. You think you found it in 12? Okay. I may have found it here. 1 U.S. fluid gallon, which this would be, is 4 U.S. fluid quarts. We knew that. 8 U.S. pints. We knew that. 128 U.S. fluid ounces. Okay, we could calculate that. Ha! And here we have it in cubic inches and cubic feet. You see it? Okay. Which do we want? Cubic feet. That's the one I think the book seems to like to use as cubic feet. So what I'm going to do is use that 0.134 cubic feet. 1 gallon is 0.134 cubic feet. Okay? Now, that makes the weight density pretty easy to calculate. What would it be? I don't know how I managed to do that. I managed to get my string here wrapped around this cord. I never intentionally do it, but it's always like that. Okay. What is your density, weight density? What's the formula? F sub W, the weight, divided by volume. And this is, by the way, your volume. Okay, in cubic feet. They do? Shame on them. Everything else they've been doing, but their final answer. See, they did it the long way. Their final answer is in pounds per cubic foot. You see it? So they've been doing dumb, okay? So what is this? Their weight is 8.34 pounds divided by their volume, 0.134 cubic feet. Okay? And what do you get? $62. What did you get? 23? Is that what you said?
Yes.
Okay, 62.23. Is that what you said?
Yes.
Okay, now they get 62.4. Now what that tells me is this is not a very precise conversion. Okay? Because that is, the standard is 62.4. That's what you always approximate. But this would be 62.2. The other way gave it 62.4. It's not that that's any better. It's that he used a bad number there, I think. My guess is that rounded poorly. That may have been a 0.36 or something like that, that they put a big round on it, and therefore they came out with a much smaller number, or something like that. Okay, maybe 0.44, you know, 1344, and they rounded down. Whichever they did, either answer would be okay, pounds per cubic feet, or using it the other way, pounds per cubic feet. It's just that anytime you use the rounded number, you're going to expect to get some imprecision. Okay?
So if you do this on the test, you're not going to...
Yeah, if you're that close, you're going to get credit. Okay. Okay. If you were 61.4, now you're off by 1, so you're going to only get a little bit taken off, Yeah. Okay. I don't know. They just use a poor number, I guess. All right, let's move on to example 4. Can I erase this one? Example 4 is find the weight density of a can of oil, 1 quart, weighing 1.90 pounds. So again, we're looking for weight density. That's D sub W. And that is the weight, which is F sub W. That's the one this book uses. I don't usually use that, divided by volume. Okay? And it said the can of oil, 1 quart, okay, of oil, and they said that weighed 1.90 pounds. Okay? Now what we have to do is figure out what a quart is. So go back to the same place we were. Now, did someone say they found another table with the answer in it? It may be some of the other tables are more better. Did someone say table? Oh, yeah, right. We were looking for volume. Okay. Yeah, that weight density table you were looking at is the same one that was on the board earlier, wasn't it? That's what I said. I ran across it. Yeah, that's the same one we had on the board. Yeah. Okay. Now, just making sure I'm not skipping it somewhere. What you would have to do here is to use the 0.134, which we know is probably not a great number, and divide that by 4, and that would give you the cubic feet in a quart. So the 0.134 divided by 4. Okay? And someone do that for me. 0.134 divided by 4. 1 quart is equal to 1 gallon divided by 4, a fourth of a gallon. And that would be 0. What was that number again? 134. I hate it when this does that. Okay. 134 cubic feet divided by 4 and that would be what? Something on the order of 0.03. Say again? 0.0335. Okay, and that would be cubic feet. All right. So now we do our weight, which is 1.90 pounds, divided by our volume, which is 0.0335 cubic feet. And what does that give us? I wouldn't be at all surprised if we don't come up a little bit less than what they do in the book, because we did last time, but let's see what we get. Anybody? Say again? 56.7. That would be pounds per cubic foot. Okay? Now, what was that again? That was a can of oil. Let's go back to our table and see what oil was. 54.2, just maybe a little bit denser oil. Actually, in the book, it had 56.9. So you see, you're much closer than the table was. So, yeah, that's going to be fine. And it's just because they use a different conversion factor. I'm not saying which one's better. Hard to say. All right. Ready for example 5? These are not much different, so they're reinforcing the same type stuff. Example 5. A quantity of gasoline weighs 5.50 pounds. So that's the F sub W, the weight, 5.50 pounds. We just don't know how much it is. Okay? With a weight density, so they told you the density, weight density is 42.0 pounds per cubic feet. 42.0 pounds per cubic feet. Okay? Find the volume. So what we're looking for is volume now. How do we do that? Second? Okay, how do you set it up? Second? Okay, on both sides of what? Okay, you say start with the density formula. That's equal to weight per unit volume, multiply V by both sides. That sounds like a winner to do. And then divide by density, right? Okay, as long as you switch them right. And that's what doing this, that tells you exactly how to switch. Now, if the other Jennifer were here, she liked using my Navy thing. And since you know density is equal to weight per unit volume, that means if you like the triangle, which I think she did, then you put the weight up here, density here, and volume here. So if you're looking for volume, cover the volume and you get weight per unit. You see these go out, weight per unit density, which is exactly what we got there. So you don't have to do the maneuvering around, you can just use the thing. As long as you put them in the right places. And you see if that's on top there, that goes on top. So anyway, we got it. What is our weight? 5.50 pounds. And it's divided by 42.0 pounds per cubic feet. Okay? Now, the other way, and I don't know if this is what you were asking, but if you work it out so the units work out right, that's another way to do it. That's called dimensional analysis. I like to do it that way, but that's a little more involved sometimes than the other. Here, the pounds will divide away. You're left with 1 over cubic feet, so that would give you cubic feet. So someone punch in those numbers and tell me what you get. 5.5 divided by 42. Okay, let's make it 131 cubic feet. Now, is that what they give their answer in? Yes, it is. Okay. I thought they may change it back to cubic inches or something. But no, they left it in cubic feet. So there it is. Exactly. Does that make sense? All right. Now, this is something that we do. Actually, my physical science class, we did it just about a month or two ago. We had some basalt, which is a fairly dense ocean rock. It's a black rock, has a lot of iron in it. And we had a piece of granite. A piece of granite was much bigger than the little pieces of basalt we had, but we calculated the density of each of them. Sure enough, got the density of basalt was a little bit greater than that of granite, which you expect because it has more iron in it than granite does. So that's what they're telling. This is exactly how they did it. The density of an irregular solid or a rock cannot be found directly because you can't say, oh, here's its length, width, and height, because it's irregular. It doesn't have that. It's not a sphere. It's not a regular shape that we have a formula for. So what we do is we find the amount of water that it displaces. So what you do, you fill up, what we did was just a beaker with water and make sure it's absolutely full. And then gently, and have a larger container underneath that, lower the rock into it, water spilled out. We caught all that water and then measured it in a graduated cylinder, telling us how much volume of water, and that was the volume of the rock. So that's what they're telling you to do, which is the same as the volume of the irregular solid. The volume of water in the small beaker equals the volume of the rock, using the picture they have there. So that's how they've gotten these numbers. Let's see what we do with them. A rock of mass 10.8 kilograms. So the mass of the rock is equal to 10.8 kilograms. Okay? You can write that on a scale and get that. Displaces 3,200 cubic centimeters of water. Okay. Now, I sort of want to go back and show that table again, but it would mean getting out of this slide, going back to another slide, and then we'd have to redo all this again. So if you just turn the page back and notice the density of water, it's 1,000 kilograms per cubic meter, right? And how did I tell you to get that to grams per cubic centimeter? Move the decimal 3 places. Okay? Maybe that's not what we want to do, though. Did I write that down right? Yeah, that's a line over it. Okay, I was thinking that's a weird-looking number there, but that's a 0 with a line over it. Okay, so I don't want to do that. Because what let me go back. What we're looking for here is the mass density of the rock. So we don't want to go back the other way. We want to do it this way. So what we want to do is make that 3,200 cubic centimeters into cubic meters, because we want to get the mass density. Okay, you tell me, what's the mass density of the rock? What's the formula for it? Formula for mass density. Mass per unit volume. We know the mass, we're looking for the volume. Well, this is the volume in cubic centimeters. Okay, we want the volume in cubic meters, right? So we're trying to get this to cubic meters. Okay, so what unit will we put where? Okay, put centimeters in the bottom, meters on top. Now we match the numbers with the units. How many meters in a centimeter, or how many centimeters in a meter? You know that, right? Which? 100, which one? Yeah, 100 centimeters is exactly 1 meter. Just think of a penny. 1 cent, 100 cents makes $1. 100 centimeters makes a meter. Okay? Think of it that way. So now, but these are cubes. So you got a cubic meter over there, you got a cubic centimeter over here, so you have to cube that. I can do that and cube that. What would that be cubed? Does anyone know? You don't even need a calculator. What you do is triple the number of zeros. That'd be 1, 1, 2, 3, 4, 5, 6. 1 million cubic centimeters. Okay? So if you take 3,200, divide it by 1,000,000, basically you move this decimal 6 places here, you move this 3 and 3 more, that would be your answer. 320. So that's your volume. So you have 10.8 kilograms divided by 0.00320 cubic meters. Okay. That sounds like that's going to be pretty dense. Let's see. Yeah, it's a rock, so it probably will be sort of dense. What you get it to be? Punch it into your old calculators. Notice we're from the South. We punch it in. We don't press it. We punch it. They don't have any rocks in the table back there, so we'll have to see what it's close to. What do you get? 3,375. And that would be kilograms per cubic meter. Okay, let's round that to 3,380 kilograms per cubic meter. Okay, let's look at the table and see what that's approximately equal to. It's a little bit denser than concrete, a little denser than aluminum, but not nearly as dense as iron, about half the density of iron. So I'd say that's pretty reasonable. Okay? Let's see what the book got. 3,380. Oh, look at that. Even with my ugly 3 there. Same thing. See it? Any part you don't understand? Is it making sense? What's that? Right. Okay. When you're dividing by 1,000,000, you have to move this decimal 6 places to get it by the 1, right? When you're dividing this by 1,000,000, you have to move that 3 places here plus 3 more. You had a 3 here, a 0 and a 0. So that's 0.00320. Okay. That's the way I do it. You can do it other ways if you'd like, if you see it better. All right. I think this is a different rock, so we'll erase everything here. All right to erase it? Okay. Example 7. A rock displaces 3 gallons of water. Oh, here we go again. So a rock displaces 3.00 gallons of water. Okay? That's not grams, gallons. Gallons of water. And has a weight density. So this is the capacity. I want to say volume. I'll put it as volume, but it's really a capacity of water. Okay? The weight density, which is D sub W, is equal to 156 pounds per cubic foot. Now that's the density of the rock. They really, it's okay the way they wrote it. So the question is, what is its weight? So what's the first thing we've got to do? Convert the gallons, 3.00 gallons, to what? Volume in cubic feet. Okay, so that's what we've got to do. So what unit is going to go where? What unit goes where? Always put the units in their place. One goes on top, one goes on bottom. Which goes where? Help me, help me. Huh? Go ahead, say something. Anybody? Say again? Yes, of course, because they have to cancel out. And they put cubic feet on the top. We go back to our table near the back of the book. That one that gave that. I just have to find it again. Yes, that was 0.134. 1 U.S. gallon, U.S. fluid gallon, is 0.134 cubic feet. Okay? So 1 gallon, 0.134 cubic feet. So this time we multiply because they're in the numerators. So 3 times 0.134, I can almost do that in my head. That would be a 2, that would be a 0, and that would be a 4. 0.402. Is that right? Okay. 0.402 cubic feet. So, okay. What are we looking for? The weight of the rock. We hadn't figured that out yet. How do we get weight of the rock? What's your basic formula? Density is equal to weight divided by volume. The weight density is weight divided by volume. So we're looking for the weight of the rock. So how do we get it? Multiply both sides by the volume. Right? And there we have it, right there. The weight of the rock is its volume, which is 0.402 cubic feet. Multiply that by its density, which is 156 pounds per cubic feet, per cubic foot. Notice your cubic feet go out, which is good. And what do you have as your answer? 0.402 times 156. It's going to be about 30. I don't know, I'm guessing. Do the math. What you get? 62, okay. Yeah, 4 times 15 is 60, okay. Say again?
62.71.
Okay, let's round that to 62.7 pounds. Okay? And let's see what the book got. I bet you it's a little bit greater. 62.6, a little bit less. So you see, you're close, really close. They went a roundabout way to do it, which I found is rather bizarre. Okay. Any questions? Okay. Now, a new concept. Yeah.
When we were doing the crossing out earlier, when
Right.
we were doing we divided to get the volume, we divided last time
Yeah. We had volume is equal to weight divided by density. Right. Okay.
Here we multiply.
Well, because you're looking for weight this time. Okay, you do what the things tell you to. If you're looking for volume, you did the very same first step, but then you had to divide by density so you would get volume by itself. This time you wanted weight by itself. All you have to do is multiply by volume. Yeah. If you let the units take care of you, and you see the units cancel out perfectly to give you pounds. Yeah. Got it? Good deal. Good question, by the way. All right. Now, before we can go on to example 8, there's one little thing we got to do here. Can I go on a race? Everybody? Got it? Okay. Is a definition. To compare densities of two materials, we compare each with the density of water. And that leads to something we call specific gravity. Okay? The specific gravity of any material is a ratio of its density to the density of water. So, specific gravity, and that's what they use too, SPGR, I didn't know they did, is equal to the density of the material divided by the density of water. Okay. Don't put D sub W, that would be the weight density. This isn't weight density, it's the density of water. Now this works if you're dealing with mass density or weight density, but you have to use both of them in the same thing. You can't use the weight density of the material and the mass density of water or vice versa. You have to use the weight density of one and the weight density of the other, or the mass density of one and mass density of the other. So it doesn't matter which density you use as long as you use that same density in both of them. And what it winds up is specific gravity has no units, because your numerator is either going to be grams per or kilograms per cubic meter divided by kilograms per cubic meter. Those units divide out, you have no units. Or pounds per cubic feet divided by pounds per cubic feet. Those units divide out and you have no units. So specific gravity is what we call a dimensionless or unitless quantity. So let's move on to example 8. The density of iron, so I'm going to call that D sub Fe, okay, is 7,830 kilograms per cubic meter. I really don't like those units, but that's what they use. Find the specific gravity. So we want SPGR for Fe, okay, for iron. How do we get that? The density of the material, which they just gave us, right? 7,830 kilograms per cubic meter divided by the density of water. So go back to your table, but you should remember that pretty easily. Density of water is 1,000 kilograms per cubic meter. You got to use the same units you did before, and you see that is 1,000 on the nose. Okay? So divide that by 1,000, and that's also in kilograms per cubic meter, taken from the table. The units go out, and you just move your decimal 3 places here, move that decimal place 3 places there. 7.83 is the specific gravity. No units involved. Do you see that? Now, do you see now why I like to use grams per cubic centimeter? That's exactly the same thing you would get with a specific gravity. Same number, the density in grams per cubic centimeter would have those units, grams per cubic centimeter. If you wanted to go to specific gravity, just throw away the units. Same number, it's just dimensionless, whereas the density actually has dimensions, grams per cubic centimeter. So that's why I like that measure of density far better than kilograms per cubic meter. That's a huge amount. You never have a cubic meter of anything, usually. Maybe air, but that's about all. Now, I've told you before how big a cubic meter is, right? Okay. I need to get up and walk anyway, so this is good. Okay. This door, the standard distance from floor to the doorknob of most doors, they're almost always the same height, right? That's right at a meter. Okay? So if that is about the same as the width of the door, that would be a square meter. So I come out 1, 2, 3, about that many blocks, that would be a cubic meter. From the doorknob over there to here. If that was full of water, you know how much that water would weigh? A ton. Okay? Who wants to mess around with a ton of water? I don't. Okay? I don't want to mess around with a ton of anything. So that's why I don't like using cubic meters as your density thing, because that's such a huge volume. The cubic centimeter, that would be like your little fingernail. The width of your little fingernail, wide, high, and deep. That's one of those little bitty sugar cubes, right? I like using cubic centimeters. And then the number you get for grams per cubic centimeter is exactly your specific gravity. It's just the specific gravity doesn't have units. All right, but that's my little harping. So 7.83, that's it. That means that iron has 7.83 times as dense as water. Thus, it sinks in water. Okay? Most of the time. Okay. Let's go to example. Ooh, can we get in example 9? Let's try. Okay. The density of oil. Oh, can I go to a new page? Okay. The density of oil, and this is weight density, by the way. Density of oil is 54.2 pounds, I can't write, per cubic foot. Okay? Find its specific gravity. What is specific gravity? It's the density, weight density of the material divided by the weight density of water. Okay? If you're using weight density of iron, you have to use the weight density of water. So that would be 54.2 pounds per cubic foot divided by, and go to your table, you get the weight density of water. What is it? It's on page 330. Weight density of water. In that table. Find water, go across to the third column. What's that? 62.4.
Oh, you said weight
We did the wrong one. And I thought about it after.
So you have to use the same units. Okay? And now the units go out. And what is the specific gravity of oil? I think that's what it was, wasn't it? Yeah. Anyone do it? 0.869 with no units. Okay, now, let's confirm that, or at least see how close it is to what's in the table. In the table, they don't have the mass density in grams per cubic centimeter, but they do in kilograms per cubic meter. Remember, you moved the decimal 3 places. So that'd be 869 kilograms per cubic meter. Let's see what they have oil in the table as. 870. That's pretty close, wouldn't you say? So you see, just move that 3 places over, the decimal 3 places over here, you have your weight density, your specific gravity. Just leave off the units. Okay, let's see what they got. 0.869. Good for them. That means oil is 0.869 times as dense as water, thus it will float on water. And we know that to be true, don't we? Yeah. An oil spill, that sheen, the mess is at the top, okay? And sometimes the way they do oil spills is not the nicest way. They just set it on fire, and then it burns because it's all on top of water. And then the water puts out the flame when it burned up all the oil. So pretty good way. It just makes a mess and it's nasty. Okay. All right. We came close to wrapping up. So I'm going to, I need to erase that. We'll start next time. Where is my, I've lost my marker. Oh, here it is, I think. Nope. Is it? Nope. All right, folks. Is it under here? There it is. Yeah. All right. So how did we do? Yuck, we came so close to finishing. I think you could do most of the problems in 12.5, the odd numbers, 1 through at least 31, 33, 35, something like that. And maybe all of them. And then at the end of the chapter, you have review questions, which are multiple choice, which are okay to look at. And then you have review problems. And I think, are all those answers in the back or just the odds for review problems? I think all the review problems are in the back. So any of those would be good to do. All right. Now the question I have for you, since it's going to be a whole week before we meet again, and we almost finished the chapter, do you want me to go on and give you the third test? Second? Yes. Okay. Let me see if I can find it. How many people we got in here? Okay, I only have one. Let me see if I can get the I can get into the office. Let me see if the copier is up. How many people do we have now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think we're down to 11 people, if I'm not mistaken. I've got one. Does anyone need to leave right away? I've got one copy while I can make copies. Anyone need to go? Okay, who wants this one? Okay. Now hang on. I may have some corrections to make. Let me get the copy. Very good. Will any of you see any of the other students before next week? You got one. Okay. Now let me see, does yours have corrections on number 3? Okay. Okay, here's what number 3 is. Now, I wrote them in. If you notice on number 3, a vertical steel column of office building each support a weight of 50,00. That makes no sense. They need an extra 0 there. That's 50,000, not whatever that says. And then the B part of the question is 60,000. They say 60,00. What is that? Okay? It makes no sense. I think the rest of them are okay. All right. Good deal. All right. Then we will pick up from there next time. So we have a little bit to go in this chapter. Not much, but you can work on those and start working on your test if you like. Good deal.